My public service announcement is mostly for US audience. So if you are eligible and you have not yet, please go vote. And if you have already voted, please check that your vote was counted. I think lots of states have websites to do it. And maybe a bit more selfish promotion that I want to do is advertise this initiative with AMS that I'm co-organizing with Matt Ando, Justin Lanier, and Marissa Loving, called Paradigms. And so this is focused on diversity in graduate mathematical sciences. And our kickoff event is a conference November 20th through 23rd. And so you can look at the AMS Paradigms website. I'll write that here. And you can also register on IMSI's website. This is a new math institute based at the University of Chicago. Okay, so now let's get back to the topic at hand. So everything I'm speaking about today is joint work with Brendan Kreutz, and it is in progress. I'll mention the things that we're still hoping to do when we get to that point. So what is a sort of broad motivating question I want to consider? If we have a smooth projective geometrically integral variety in some projective space, Pn, and say it's a degree D variety over some field. Right now I'll be agnostic about the field, but I am a number theorist by training, so local and global fields are closest to my heart. So then we all know that slicing with a general plane of complementary dimension will give us a zero cycle of degree D on X. And in fact, it gives us not just a zero cycle of degree D, but an effective one. And so some questions that I want to touch on today is whether this is the best that we can say. So for instance, if you're fixing the degree, the ambient dimension, and the dimension of X, can you find such an X over a field K where the best you can get, the smallest effective zero cycle is degree D, or maybe just the smallest zero cycle period has degree D, smallest positive degree of a zero cycle. And as I mentioned, so we can be agnostic about the field in the beginning, but I'm also particularly interested in what happens over local and global fields. So I'll also want to know how this question varies when you restrict the field. So again, the setup is we fix the degree of our projective variety, its dimension, and the ambient dimension, and is there a way that we can do better than the points you just get by taking a hyperplane section? Well, if you look at curves over number fields, this is best possible already just by looking at genus 1 curves. So by results on constructing curves with specified period or index, you can basically show that you can find, you can always find an elliptic curve with an element of specified order in its Tate-Shafarevich group, or sorry, not just in its Tate-Shafarevich group, in its Weierstrass group. And so then that will give you a genus 1 curve of the desired period, and which will map to this question. Will tell you that the smallest degree of a zero cycle on that curve is what you get by slicing by a hyperplane section. But this comes already just from looking at genus 1, and in genus 0 for curves, it's not so interesting because every genus 0 curve can be embedded as a plane conic, and so there's sort of not much room for interesting things to happen. So if we look at negative codirer dimension and higher dimensional varieties, then we see that this is not best possible. So if we look at geometrically rational surfaces, then often geometrically rational surfaces have points of smaller degree, points that you don't just get by slicing with a hyperplane. So let's just review some of those. I'm going to stick to looking at Del Pezzo surface of degree D for D greater than or equal to 3, because then these surfaces, the anti-canonical embedding does embed them as a degree D surface. in projective space, analogously to what I was considering on the very first slide. So let's just go through what's known for these. So degree 9 Del Pezzo surfaces, these are all Severi-Brauer varieties, and they're index 3 Severi-Brauer varieties. So by some classical results about Brauer classes, these are all cyclic and therefore always have points over cubic extensions. So what I want you to notice is that 3 is less than 9. So slicing with a hyperplane gives us something of degree 9, but we actually get something smaller. Again, also for degree 8, sometimes you do even better than this, but at least you always already have quadratic points. Even though this embedding, it's sitting as a degree 8 surface, we still get degree 4 points. And if we look at degrees 7 and 5, well, these are well-known results that over any field, Del Pezzo surfaces of degree 7 and 5 always actually have rational points. So those we definitely don't get just by slicing with the hyperplane section. So these degrees 9, 8, 7, and 5, those are ones where we do know that this is the best possible, not the best possible result. But then for certain surfaces we do. So for degrees 6 and 3, there do exist surfaces of this type where we do have sort of the lowest degree 0 cycle that you get is the one from slicing with a hyperplane. And of course, to prove this, you give examples. So I know definitely that there exist examples in both of these cases over local and global fields. But for instance, this cannot happen but not over C1 fields. Okay, so when something is best possible, it's usually best possible for a particular type of field because we have to give a construction for it. Okay, and then you'll see that there's one missing, which if you remembered my title, you might have guessed. And that for degree 4, it's not, is not known. So over local and global fields, all existing examples in the literature have actually have quadratic points. So again, the comparison that you're supposed to look at is that that's degree 4, but in the examples we get degree 2. But unlike the other cases that are written in black, there's nothing in the literature that proves that it always has quadratic points. Okay, so now I'm going to focus looking on this question. And as many of you will know, Del Pezzo surfaces of degree 4 can always be given as an intersection of 2 quadrics over some field. And I'm just going to throughout avoid working over fields with characteristic 2. And so what we've reviewed is that we know we have an effective 0 cycle of degree 4. And what we want to ask is, okay, do we know with no other assumptions that we always get a 0 cycle of degree less than that? And if so, is there an effective 0 cycle of that degree? And again, the question is close to my heart. Does this answer change if K is a local or a global field? So together, the theorems of Springer and Ammer and Brumer show that on intersections of 2 quadrics, we have a 0 cycle of degree 1 if and only if there's an effective 0 cycle of degree 1. And I just phrased it that way to mirror what I've been writing. But of course, normally that's written as you have a 0 cycle of degree 1 if and only if we have a rational point. So we know exactly the criteria to have a 0 cycle of degree 1. That's the same as having a point. And definitely over local and global fields and over many non-C1 fields, you can write down an intersection of two quadrics that doesn't have a point. That's not too difficult. So for instance, if you can already write it down one quadric without a point, then you just do that and set your second one to be whatever you want. So we know what can happen for degree 1. So really the question is just about when do we know that we get 0 cycles of degree 2 and effective 0 cycles of degree 2. And just, I don't know, for shorter language, so the smallest degree of a 0 cycle on X, that's called the index. So I'll replace the question, do we have a 0 cycle of degree 2 with just does X have index dividing 2? And to know if it's effective, that's the same as having a quadratic point. Okay, and just to remind you, I guess I really wanted to emphasize this. I forgot it was appearing on so many slides. Okay, so what's known now for intersections? Remember, this is for X is an intersection of two quadrics. A smooth, complete intersection. And Pn. Okay, and I'm going to do this over local and global fields. Over non-Archimedean local fields, because I think you can figure out what happens for Archimedean fields. Okay, so if n is at least 8, then Demjanov proved in 56 that for a p-adic field, the index is always 1. And so also we know already that that's the same as X having a rational point. So once we have two quadrics in p at least 8, then we always have a rational point. And when n is at least 5, conjecturally knowing what happens p-adically is enough to tell us what happens globally. So conjecturally in this case, X always satisfies the Hasse principle, and that tells us that the index globally is just going to be the LCM of the local indices. So if we understand what happens locally, then we can conjecturally we can control it globally. And this conjecture was proved very recently by Heath-Brown when n is at least 7. Okay, if we go to the other extreme, if we look at n equals 3, so again, this is the case of curves that I talked about at the beginning. So we should expect here, well, we did have a best possible statement before, so definitely index can be 4. And also, just to relate it to other things that I'm talking about, the index does not have to be the same. That you can have examples that violate the Hasse principle. Okay, and now the, okay, so this is n equals 4, the dimension, but this is again the del Pezzo surface of degree 4 case. So this is the same case that came up before as the unknown question mark. And so here we don't know what happens. So the index doesn't have to be equal to the LCM. And we don't know what either left-hand side or right-hand side could be. So this case of intersections of two quadrics in P4 or del Pezzo surfaces of degree 4 sit in sort of two families of things as kind of cutoff points where we don't know what happens. So if we look at the del Pezzo surfaces of degree D, this is the case where we don't know if we can do better than just slicing with hyperplanes. And if we look just in intersections of two quadrics in Pn, when n is at least 5, we expect that X satisfies the Hasse principle. But here we don't know what happens. So it seems possible that maybe you could have this index be equal to 4 and the LCM of all of them be equal to 2. And so sort of all of the possible values that could appear are appearing for a single single surface. Okay. So what do we prove? So here now I'm looking at the intersection of two quadrics in P4. So that's my N. Okay, so first we show that actually you can get index 4 over a big enough field. So our example is over an algebraically closed field and then iterated power series. Sorry, iterated Laurent series. So over this very large field, we do show that there exists del Pezzo surfaces of degree 4 with index 4. But if we restrict to fields of arithmetic interest, then this no longer happens. So if K is a local field, or if the true torsion of the Brauer group is 0, then X always has a quadratic point. And in addition, if K is a number field, so let's just ignore what's in orange for now, then we should get that the index is 2, and conditional under Shinz's hypothesis, we actually always get that X is a quadratic point. So this fact that all of the examples in the literature had quadratic points seems to not be an artifact of what types of examples they were considering, but it seems to be the case for all del Pezzo surfaces of degree 4 over number fields. Okay, so what is in orange is currently the assumptions under which we can prove this. I'll explain a little bit more how the Brauer group comes up. We have done what feels like extensive searches, even when this hypothesis is not satisfied. And the same results always seem to hold, but yeah, a search is not a proof. So we still need the orange hypothesis in there right now. Okay. Right. I'm just going to pause if there are any questions and take a sip of my coffee. Okay. Let me just go on a little bit. So as a byproduct of our proof, we realize that the statement that we have is equivalent to a statement. Oh, this is showing up in the wrong order. Let's just display everything then. Okay. Is equivalent to a statement about certain types of Savary-Brauer vibrations having rational points. So now we leave del Pezzo surface of degree 4 land and we just look at, now this is going to be, well, in general, a higher dimensional family. So we just have a family of varieties over P1 where the generic fiber is a Savary-Brauer vibration. And I want at most 5 degenerate fibers, and that the generic fiber is 2 torsion in the Brauer group. So it could be a conic bundle with 5 bad fibers, but it could also be a Savary-Brauer vibration where the fibers are higher index. And in fact, the way that this arises most naturally is we get a family of 3-dimensional Savary-Brauer varieties. And then for these types of Y, these bottom 2 results should look visually similar, I hope, to the conditions that I had on the previous slide. And instead of looking at quadratic points on X or the index, here where, oh, sorry, this should be index 1. So you always get a zero cycle of degree 1 on these vibrations. Okay, and then similarly with how we construct a del Pezzo surface of degree 4 that has index 4, we also construct such Y over the same type of field, these iterated Laurent series fields that do not have index 1, that have index 2. So this is this phrasing struck me as particularly interesting because it's a fairly nice algebraic class of varieties where we know it should have points over local and global fields, but it doesn't have points in general. So most other varieties that I know of this type, we saw del Pezzo surfaces of degree 5 and 7 always have rational points, but that's over any field. And conic bundles with 3 bad fibers always have rational points. That's also over any field. So these types of varieties have rational points or should have rational points over local and global fields, but not over general fields. So this is a more sort of subtle arithmetic property that is leading these varieties to want to have points. Okay, so let me say a little bit about how the proof goes, at least in the, well, I'll talk more about the local field case. So what we prove is that if you have no rational points on X, then the reduction, I mean, usually we expect if you have no local points, then the reduction needs to be very special. But often you have to account for things like maybe small residue fields, and your residue field is just not large enough to have points, or you just, all the points over the residue field are in the singular locus, and maybe you have particular kind of singular loci. But here, we get to restrict very strongly what the reduction looks like if you have no rational points. And in particular, we show that the reduction is always what's called non-split. So it means that the reduction has no open geometrically integral subschemes in it. Another way of saying this is that that if x mod pi is reduced, then we need x to be irreducible but not geometrically irreducible, so that there are the geometrically integral subschemes are only defined after an extension of the ground field. So you can't sort of have points defined on them. Okay, and the way we do this, the way we're able to do this is that we leverage the result that I mentioned at the beginning, the Springer and Ammer-Brummer theorem. So we know that if x of k is non-empty, then that tells us that we have no points over any odd degree extension. So in particular, we have no points over any unramified extension of odd degree. And so by taking arbitrarily large unramified extensions of odd degree, we can make the residue field, we can assume that our residue field is arbitrarily large. And so we don't have to worry about these small residue field arguments that one normally runs into when trying to study varieties over local fields. So this bypasses the problem. Of small residue fields. Okay, and then from the proposition Now this is basically a classification argument. That there's basically only two different ways really that your variety can be non-split, and then we just study those, find particularly nice models by using these semi-stable reduction arguments of Kolar and Tian, and then show that, well, over certain quadratic extensions, those varieties will obtain quadratic points. Okay, so yeah, there's really two main pieces that we get to bypass this problem of small residue fields, and then this condition of being non-split is so strong that it makes a classification argument feasible. Okay, so that's the local field case, and maybe the local field one is not so surprising because varieties over local fields want to have points, and so it's just determining where the cutoff is. And so for del Pezzo surfaces of degree 4, we always get quadratic points, but that transition will happen somewhere. So that is maybe not as surprising. Okay, I think the surprising part really comes from the results over number fields. So let's talk about how we get there and how these Savary-Brauer varieties come up. So basically what we show is that if you look at sim2 of x, so that's singular, but you can find a smooth birational model that is a Savary-Brauer fibration of three-dimensional Savary-Brauer varieties over P1, where the generic fiber is true torsion in the Brauer group. And what is the argument? The argument is, I don't know, something that we see a lot. So sim2 of x, I can think of a point in here as just giving me 2 points on x, maybe Galois conjugate. And so I can look at the line that I get by joining these 2 points inside of P4. And you can show that this line must lie on one of the quadrics in the pencil. Okay, really this should be projective. So the way you get this Savary-Brauer fibration, this is the Fano variety of lines on the quadrics, defining the pencil of quadrics defining the del Pezzo surface. Okay, and these types of Fano varieties are very well studied, and what you can, from their study, one of the things we are able to deduce is that there is a very tight connection between the quadric fibrations defining X and this variety G. So this is a quadric fibration whose base locus gives X, and then we have G. And these two maps, they have the same bad fibers. So that tells you that there are 5 of them coming from the rank 4 quadrics in the pencil. And over G, so if GT is singular, then it is geometrically reducible. And the field extension that splits the fiber is equal to the discriminant extension of the corresponding rank 4 quadric. Okay, so sort of all of the information about G can be read off from Q, and vice versa. There is a result that was observed by Victor Flynn and then worked out in more detail by Skarbogatov that says that if you start with something that looks like G in the Brauer group, so you have a two torsion element in the Brauer group of a generic fiber, and you have 5 points where it ramifies or degenerates, and then you have these quadratic extensions that give you that. From that, you can construct Q. So what I explained over here is the construction from Q to G, but we can also reverse the arrow. And so that's why this rephrasing in terms of these G's is actually a rephrasing and not an implication. Okay, I think I want to say a little bit more on this. So just add another page. Maybe I can squeeze it in here. Okay. And one thing that we were very excited about when we saw this is that these types of fibrations, these fibrations of severe Brauer varieties, where we have controlled bed fibers, conjecturally, we know exactly when these have rational points. So conjecturally, the Brauer-Manin obstruction is the only obstruction for these rational points. So this is the so-called Brauer set that implies that we have rational points. This is conditional on Schinzel's hypothesis. And this is, I think in this generality, we need the full strength of Harpaz and Wittenberg. And Harpaz and Wittenberg also show that we get a similar statement for 0 cycles of degree 1, but it's unconditional. So I just don't want to write out what it means to have the Brauer-Manin obstruction be the only thing for 0 cycles of degree 1, because that gets a little notation heavy, but just the upshot is that we completely understand how to check whether a fibration, whether G has a 0 cycle of degree 1, and we can do it almost completely locally, just with a small global input that comes from looking at the Brauer group of G and computing this so-called Brauer-Manin obstruction. Okay. I never know how to register how a talk is going on Zoom. So I'm just going to pause in case anybody wants to take time to unmute their microphone. It's also okay if there are no questions.
Any questions for Bianca?
Okay. So what is this Brauer-Manin obstruction and how can we start getting our hands on it? And then what is the difficulty that is still leading to this orange hypothesis that we have? Okay, so what is the Brauer-Manin obstruction? Okay, so let's fix some alpha in the Brauer group of X. So then, given any irrational point on X, so that's a map from spec K to X, so I can pull this Brauer class back along this map. So this is the map P, goes to P upper star of alpha, and that lands me in Brauer K. Okay, and similarly, so if I look at the set of adelic points, so what is this? This is just the product of points over every completion. And so I can do the same thing here for each collection of points PV. I can just take the collection of Brauer classes where I pull back that point. And so I land a priori in the direct product of the Brauer group of the completions, but actually I can prove that I land in the direct sum. And then because K embeds into its completions, we have two diagonal maps on the top and on the bottom row. So I just diagonally map the Brauer group of K into the Brauer group of KV for HV, and I consider a rational point as a v-adic point for each one. And then, well, I think you can see that this whole diagram commutes. Well, this beginning bottom map, oh, I should not have done that. That is too dark. Here's my undo. Okay, let's. Here, this bottom map, this is what gets studied in the, let's say, fundamental exact sequence of global class field theory. So if you love class field theory like I do, then your instinct is to just fill this in with a nice exact sequence. I understand that this is the algebraic geometry seminar, so there might not be as many lovers of class field theory here, but it's okay. I love it enough for all of us. And so then we see, just from this diagram, if we had an adelic point that came from a rational point, then when I map it down and over, it actually has to land in 0. So this gives us a condition. So what I just showed you with my laser pointer is that the rational points all land inside the set of points that map to 0. So we often think of this as a pairing from the Brauer group to the set of adelic points. So we describe this, all the things that map to 0, as the set of adelic points that are orthogonal to a Brauer class alpha. And this is true for all alpha in the Brauer group. So what I really get is that the rational points live inside what is called the Brauer-Manin set, which just by definition is the set of all adelic points orthogonal to every element of the Brauer group. Okay, and this imposes a compatibility condition. So you could think of this as if you wanted to do the Sun Tzu remainder theorem, but for all primes and the Archimedean place, instead of just for finitely many primes, you couldn't just always do it for free. You have an extra compatibility condition which has to come into play, and it's given by this Brauer group. So that's like morally how you can think of this, that this is an extra thing that has to be able to hold to extend something like the Sun Tzu remainder theorem to all places. Okay, so this is the Brauer-Manin obstruction. And as you might see from the definition, well, formally you can see what happens, but you probably have no sense of what this map phi sub alpha does. So if I hand you a set of adelic points, and it's true, there's not a necessarily easy way to compute this. We really have to have good control over what this alpha in the Brauer group is. So to be able to compute this obstruction, we really need to have good understanding of what the Brauer group of X is. Okay, so now let's talk about what those are. So X remember, is given by the intersection of these two quadrics, but those particular two quadrics are not really important. Really, what X is more naturally associated to is this quadric fibration. So it's supposed to be a curly Q. So these two quadrics really cut out a vector space of quadrics, and the X is the base locus of that pencil, but I can also just consider the whole quadric fibration. And the whole quadric fibration is what I told you has a nice relationship to G. So the bad fibers are the same, and these quadratic extensions that are invariants of the bad fibers also match up in both cases. And this fibration is also what can be the Brauer group of X and the Brauer group of G can be read off. From the fibration. Okay, so what are these sets? So, okay, so the part that really depends on X so inside the Brauer group of any variety is something you get by just pulling back the Brauer classes on the ground field. If you have photographic memory and remember exactly what I had on the last slide, you could retrace it and see that the elements in the Brauer group of X will not cause an obstruction. So the Brauer-Manin obstruction really depends on this quotient. Probably you don't have a photographic memory, so then you can just believe that what I'm telling you is true. Okay, and that's the same thing for the Brauer group of G. And these two sets, what we know is that they are, in some sense, canonically isomorphic to what do? We take 2 points in, so let me let S be in here, be the singular locus of the fibrations. Okay, so I told you it's the same for both maps, so it doesn't matter which one you consider. So the Brauer group is in bijection with pairs of points in the degeneracy locus, such that, well, one, this set of pairs is Galois invariant. So either they're quadratic conjugates of each other or they're both rational points. And these quadratic extensions that I was telling you about, so the quadratic extensions that split the bad fibers, they have to be the same for both rational points. So it's the same quadratic extension that is either the discriminants of the two quadrics or is splitting these two components. Okay, and they're sometimes you have to quotient if sort of there's a strong coincidence between other parts of the singular locus, but let me not worry about that too much. So what I want you to take away from this is this Brauer group, which really is controlling whether or not we have a point over the global field. It is being, that in turn is being controlled by singular quadrics in the pencil that have this particularly nice property. That together they're k-rational and the discriminant extensions of both of them are the same. Okay, and this should, so if you just wrote down sort of a random collection of quadrics, you shouldn't have this occur. So generically, we should have no Brauer group, and then we just need local points, which we have already. So the, so let me just write that down too. So generically, the Brauer group of G mod Brauer 0, which is the same as Brauer X mod Brauer 0, is trivial. So the Brauer-Manin set is just the set of adelic points, and then the result that we want already follows from what we've proved for local points. So in the generic case, there's nothing extra to show. The work that we did already in the local case, combined with all of the work that people have already done to connect adelic points to rational points, then gives us the result we want. So our focus is only on what happens for sort of special quadrics. And I don't want to get into too many details of what is happening and how we show that this Brauer set is non-empty in the non-generic case. But let me just give you an idea of sort of a problem that arises that makes this messy. To move all the zoom controls out of the way so I can write up here. Okay, so we already saw in computing the Brauer-Manin obstruction, this fundamental exact sequence is very important. So this fundamental exact sequence, it encodes quadratic reciprocity, it encodes higher abelian reciprocity laws. It's just like a thing that, at least as a number theorist, this is like all is right in my world when this holds. Okay, so what happens when we pull back this sequence to the Brauer group of X? So just by definition, this lands inside Brauer 0, and this is surjective onto Brauer 0, and this is now surjective onto Brauer 0 of XV. And then here, well, I can control what the kernel is, so I can just make a surjective map for Q mod Z. But one thing that is supremely annoying is that this map can be injective while this can fail to be injective. And when this fails to be injective in exactly the right way, so you could, I mean, you could draw maps here, and I'm going to put them in as dotted arrows. This it no longer even has to be exact. This does not have to be a complex. So like maybe a tagline is that you can think is that when you pull back to X, like quadratic reciprocity, it doesn't really hold anymore. Or if it holds in a weird way. Okay, so that is just more of a like moral statement than a precise statement. The precise statement is that this set does not have to be a complex, that, yeah, you can't, what probably you really want to do, and what I really want to do is just take this exact sequence and write it with Brauer zeros. But we can't do that. And so basically we have currently two different constructions. So when this is a complex, we have a construction of elements, that's right, in G, that are orthogonal to the Brauer set that works for all the time without this orange hypothesis. But when it's not a complex, we have to use another construction of rational points. And right now this only works when these points that I took are not just Galois conjugate, but they're actually k-rational. Okay, and we do that because we find points close to these bad fibers. And if those bad fibers aren't defined over your ground field, well, then you can't approximate them over your ground field. So right now, this other construction is what is leading us to use the orange hypothesis that I mentioned. But yeah, the need for it really comes down to this fundamental difficulty that sort of when you pull back to Brauer zero, if you don't have adelic points on X, all hell breaks loose with our normal way of understanding these constant Brauer classes. Okay. I think that's where I'll end. So thanks for your attention.
All right, so I'll give Dr. Viray a Zoom round of applause, right? Where it's one person clapping. But yeah, thank you for the lovely talk. I'd like to open it up for questions for the group here. And you're unwelcome. I mean, sorry, not unwelcome. You are welcome to unmute yourself if you have a question. And I can sort of start to get the conversation going. So you definitely laid out why we need this orange condition, right? So you just mentioned that it's like fundamentally difficult to get around this. Do you have any like, are you planning on taking it further? And if so, like, what might be something that might have a hope of working?
Right. We have a few different ideas, and some of them work, but they all require sort of more branching right now from this yellow box that I've drawn. Okay. And so that feels like, in some sense, that it's doesn't feel like the right construction right now. I mean, what I've gotten at here, that this part doesn't have to be a complex. I mean, that is sort of a fundamental thing that I can see, and that it sort of requires some branching and considering of different cases. But right now, the approaches that we have to remove this assumption, they don't feel as intrinsic as that. So we still have ideas that we're trying. I think we don't, I don't know, it's kind of like we change our minds every day, every week, whether we think we should need this hypothesis or we should not. But
and right now, where are you leaning towards? Again, knowing that this might change.
I think it's probably true that it's true even without the orange hypothesis, because we've done a bunch of examples and it doesn't seem like we're making any assumptions in the examples, but there might be something we're missing.
Yeah. Does anyone else have any questions? I will wait here until it's sufficiently awkward to get you guys to ask your questions. All right, so if there's no more questions, then I'd like to thank Dr. Viray again, and thank you for starting our day with a wonderful talk. Thanks.
Thanks.
Another, what? I'm sorry.
Oh, I just said thanks for having me.
You're welcome. All right, I hope everyone has a wonderful day or a wonderful evening. And then I'm going to stop this recording.